So please welcome to...
Thank you so much. It's a real pleasure to be here. Can you all hear me? Is that on? Yeah, I think it is now. Christina, thank you so much for the introduction. It's a real pleasure to be here. Sorry I made your life a little more stressful by being rather late in turning up, but I would have let you know if I wasn't going to make it, don't worry. So it's a great pleasure to be here. Hugely impressive endeavor, this activity of Battery 2030. I'm always still pained when you show a map of Europe to see the UK in the same shade as some of the other bits of outside Europe, but maybe one day that will be resolved in a much better way. However, let's stick with science today. My original talk title was just going to focus on one topic, and that was going to be the topic which is the first one that you see listed there, which is lithium-rich cathode materials invoking oxygen redox. Now, I'm still going to talk about that, but I've decided to only spend half the time on that, and then the rest of the time I'm going to talk about the second part of that title, which is the lithium ceramic electrolyte interface, so something on solid-state batteries. So that's the plan, and let's see how we go with it. So let's see if this is going to work. Good, and I think that also works. Fantastic. So let's start off with the lithium-rich oxygen redox cathodes. Now, I suppose many of you already know what these lithium-rich cathodes are all about. But just to recap, for those who might not, of course, the interest in them is that they offer the possibility of higher capacity and therefore ultimately higher energy density lithium-ion batteries. That's what is driving, if you like, from the sort of applications side, the interest in these sorts of materials. A lot of them are layered, but not all of them. Some have other structures too, and I will talk very briefly about the disordered rock salts. But this is the archetypal lithium-rich layered NMC material. There's the composition up there. Classic layered crystal structure of our NMC-type cathodes. These are the transition metal layers. The light blue is the lithium. So these are the lithium ions in the transition metal layers. And of course, we have lithium ions in the alkali metal layers as usual. And the point being that you have more lithium. You've got these extra lithiums compared with a stoichiometric NMC. So you have more lithium than the capacity to remove electrons by oxidizing the transition metals to their 4+ state. And so if you want to take that extra lithium out and get the extra capacity, you have to strip electrons from the oxide ions. And that's the whole point and the whole challenge of realizing these high capacity cathodes. Because if you simply cycle back and forth in this region, so this is the load curve, charge, discharge of one of these materials, make it a cathode in a cell with a lithium anode as a reference, and there's the charge and the discharge. And if you stick in this green region, which is the redox, transition metal redox region, so you're only oxidizing and reducing the transition metals, then everything is nice and reversible as usual. But as soon as you go further than that and start stripping electrons from the oxide ions, all hell breaks loose. When you come back down this way, you come back down at 1 electron volt lower in energy, so you've lost the amount of energy you can store. You really want to go back and forth along this plateau, but you have to come down here on discharge. You can cycle it thereafter like this, but you've certainly lost that energy, and there's still some hysteresis, significant hysteresis here, as you can see. And so the message is there's a big change in the voltage. That means a big change in the structure is taking place. All these things we really don't want to happen. But if we're going to be able to stop those happening, we have to understand what's happening to the oxide ions when we carry out oxygen redox. We know the lithium ions come out. That's easy in that region here. The question is, what is happening to the oxide ions? So in other words, we really need to study the evolution of the electronic structure of oxide ions when you strip electrons from them. And one of the techniques that's very powerful in doing this, and it's powerful because it's element specific, is RIX, resonant inelastic X-ray scattering. The beauty of RIX is that it allows you to excite an electron from the 1s states. It's a K spectroscopy, in other words, K-state spectroscopy. For the 1s states, in this case of oxygen, that makes it element specific to these higher states, and then it looks at emission from these electrons dropping back into these states. So if you tune into the oxygen 1s, you're looking at oxygen electrons effectively. If you tune into other 1s orbitals and other elements, you can tune into those separately. So it's element specific, and that means we can look at the valence states of the oxide ions as they evolve, as we strip electrons from them, as we charge our cathode material. So what I'm going to show you now is that load curve again. Same compound. I'll spend a lot of the time using this classic lithium-rich NMC as the exemplar, but the same thing happens in other lithium-rich compounds. We're going to go along this load curve, charge-discharge curve, and we're going to take some snapshots of the RIX spectra that we see as we do so. So if we start at this point here, this is the beginning of the plateau. Remember, this is the region where we're stripping electrons from oxide ions. Now, in RIX spectroscopy, you excite at a series of different energies, or wavelengths, and for each one, you measure an emission spectrum. So you produce these 2D maps. So on the y-axis here, we have the excitation energies. These are the excitation energies in electron volts, and this is so-called energy loss. This is the set series of emission spectra. So for each energy, you get an emission spectrum, and 0 is when you're looking at the emission at the same energy as the excitation. So you create these maps. So that's the map that you get, or the RIX, the results from the RIX measurement at the beginning of the plateau. This is the situation at the end of the plateau when we've oxidized a lot of those oxide ions, stripped electrons from them. And if you look at this, there are some changes here and here. But if I blow up this region here, or these regions here, or this region in both cases here, this is where you see the significance of the change that's occurring. There's nothing in this region before we start removing electrons from oxide ions. But after we do so, we get this series of peaks here. Now, this is basically a vibrational spectrum for the oxygen. And if you look at that red spectrum above here, this is the vibration spectrum for molecular O2. That's the vibration spectrum for peroxide, O2, 2-. And you will see that the spacings between these peaks, in other words, the vibrational spectrum that we see in this solid material after charging, is the same as that for molecular oxygen. Not for the other species, but for molecular oxygen. Now, this is a high vacuum technique. This is not oxygen in the gas phase that we're seeing. This is oxygen inside the particles of the charged cathode material at the end of charge. And then when you discharge again, here's that blown up region, nothing is there left. You're reducing that molecular oxygen again back to oxide ions. So RIX is powerful because, as I say, it's element specific. It's actually looking at the electronic states. These are cells, obviously, ex situ because it's high vacuum. You charge it up, you take it out of the cell, you put it into the spectrometer, and these are the results. So what we see is oxidizing oxide ions produces molecular oxygen, which is trapped in the particles. Now, let me say that understanding the oxygen redox process in these lithium-rich cathode materials, I think, has been one of the most difficult problems in our field. It's certainly one of the most difficult problems that I have encountered in my career working in batteries. And I want to massively acknowledge the people who have worked in this field also and made some pioneering advances in the past. They were mentioned, in fact, on that earlier slide. If I just go back to it briefly, down here, Mike Thackeray and Jeff Dan, who first recognized these materials more than 25 years ago, and they interpreted the oxygen redox as all the O2 is being lost, and then it becomes transition metal redox, and that's still got some truth, as you'll see a little bit later on. Also, Claude Delmas and Laurence in Bordeaux, and Jean-Marie and colleagues in Amiens, and of course now in the Collège de France, made huge contributions to try to understand what I think is one of the most difficult problems in this area. So I think everybody has done fantastic science in this area. And what I'm showing you today is what we understand of what's going on in these oxygen redox materials. I just want to make that really clear at the beginning. And the reason that we use RIX is because of that element-specific nature and the fact that it can probe the electronic structure of that element, in this case oxygen, which is what we need to understand if we're going to really understand what is happening in oxygen redox. Transition metal redox has been known for decades, of course, but this is the phenomenon that challenges us now. So, RIX is powerful, but it's useful to have other techniques to confirm that what we're seeing in molecular oxygen in these particles is really correct. So I'm going to show you two other pieces of completely independent evidence. The first one is this one, which is neutron PDF. Okay, so neutron pair distribution analysis. This is on the charged lithium-rich NMC material again. And the red dots are the experimental PDF pattern. The black is the fit to the charge structure. And this peak here that you see, that's not, of course, included in the calculation of the charge structure, this peak is exactly at 1.2 angstroms. That is the bond length of molecular oxygen. It is not the bond length of any other oxidized oxygen species. It's the bond length of molecular oxygen. So that's another completely separate technique indicating the presence of molecular oxygen in these charged materials. And if you don't believe RIX and you don't believe PDF, maybe you believe magnetism. So here's some squid measurements on a different material that also shows oxygen redox. It's very interesting. We started looking at this material. It's a sodium intercalation compound, but that doesn't matter. The reason we looked at this material initially was that, as I've already shown you, and as you know, in lithium-rich transition metal redox, you remove lithium ions. Some of those come from the transition metal layers, and in fact that's fundamental because, as I'll show you in a moment, those vacancies that are created in the transition metal layers reorganize to form voids to trap the O2. So that's fundamental to the formation of O2, or at least it's trapping in the particles. So we wanted to suppress that because ultimately you don't actually want O2. I'm going to talk quite a lot about it, but ultimately, as I'll show you, you don't really want to get that. You want to get true oxygen redox, true reversible hole formation on oxide ions. But we're not quite there yet. But we thought we might be able to do that with this material because this is magnesium, no lithium on the transition metal site. So this is sodium in the alkali metal layers, magnesium and manganese on the transition metal layers. And we thought magnesium might stay where it is, unlike lithium. No vacancies, no formation of voids, and therefore you can't have O2. That was the thinking. We were, of course, 100% wrong, as you can see from this load curve. You still get oxygen redox in this material. There's the plateau and the hysteresis again. I'll show you why in a moment. But the important thing is you do get oxygen redox, and this is just a line spectrum from RIX, not the map this time. And this feature here is the feature that is the signature for molecular O2. But the nice thing about this material is it is very simple in terms of spins. You can't quite make the perfect 1/3, 2/3 stoichiometry, which would mean all the manganese was already 4+. So you have to oxidize when you charge the material and take some sodium out. You have to oxidize a little bit of the manganese till it's all 4+. But from then on, you've just got manganese 4+, 3D3, and anything else that happens is on the oxygen. So it's great for doing magnetic measurements. And that's what you see here. This is a plot of the Curie constant on the y-axis as you extract sodium from this material. So the initial change, this bit in purple here, is just the oxidation of a little bit of manganese 3 because this is 0.28, 0.72. From then on, there's the experimental change in the Curie constant, those dark blue dots that you see here. Now, the dotted lines represent the predicted Curie constants, the magnetic moments that you expect evolving, depending on the nature of the oxygen species that you form when you oxidize oxide ions. And of course, there's no change if you go from oxide ions to peroxide, because they're both diamagnetic. There are no unpaired spins. And then those are the other species there. Now, what you see here is the change in the Curie constant sits on this line, which is the formation of molecular oxygen. Of course, every oxygen has got two unpaired spins. And so you can use magnetism to probe this process. Magnetism is non-destructive, non-invasive, samples the whole material equally, and there again you see evidence of O2 formation. Okay, so, and this is, by the way, why this happens here. It turns out the magnesium does move out of these layers. When you take sodium out, you go from the P to the O stacking, the octahedral stacking. Magnesium actually drops from the transition metal layers into tetrahedral sites when you charge, and that's what allows the reorganization that I'll show you in a moment that has to happen to form and trap O2. So let's come to how this O2 process can occur. We're swapping back to our lithium compound, again, our favored archetypal lithium NMC. So there's the picture we saw before, looking sideways, looking along the layers. If we, of course, look down on a layered compound, which is in this lithium-rich family, they have this beautiful honeycomb structure. If you ignore the colors of the different transition metal ions, you have this lovely honeycomb structure with lithium at its center that's typical of all these lithium-rich NMC-type materials. So if we now take some STEM images of our material, so again, now we're looking along the layers, scanning transmission electron microscopy. This is the pristine material before we do any charging. And remember, in electron microscopy, the light dots are the heavy elements from the scattering of the heavy elements. So a line along there of those dumbbells represents the transition metal layer, and those dumbbells, those sort of pairs of dots, are exactly what you expect for that honeycomb structure. So it's exactly what we anticipate from our known honeycomb structure. However, when we charge the material, that's the second image, this one on the right here, after charging, what you see is the transition metals have disordered in the transition metal layer, principally. So remember, what's happened is we've taken lithium ions out. Some of them have come from the transition metal layers. They've left lithium vacancies. The transition metals now have the possibility of reorganizing, of losing the honeycomb structure, and that's what they're doing here. That's why you get this smearing out of the light scattering. And you've now got this disorder in the transition metal layers. And these two pieces of evidence are just powder diffraction and NMR that confirm the loss of the honeycomb structure. So the honeycomb is lost, and what happens, as you'll see in a moment, is when the lithium ions go back into the structure and discharge, they can't go into those honeycomb sites anymore because they've gone. They repopulate the transition metal layers, but not in the same place, and that's the crucial point. So this is what happens. Here's our pristine material at the beginning. There's the transition metal layer, just one color now for the transition metal ions, and the light blue octahedra represent the lithiums. And they're going to be depopulated as we charge. So we charge up to the beginning of the plateau. Some lithiums come out of the alkali metal layers, some come out of the transition metal layers. That's represented by these vacancies here. Then when we go across the plateau, so far we've just balanced this loss of lithium ions by oxidizing transition metals. Now we're going to oxidize the oxide ions. And I'm representing that here. So here are the oxide ions. We're now stripping electrons from the oxide ions. Now that's weakening the metal-oxygen bond. That's why oxides are not made of O-, but O2-. So once you start forming nominally O minus, you're really weakening those bonds. You're, of course, taking electrons from effectively valence states in the material. So you're, and this is to some extent to the point. What you're really doing, being brutally, is you're decomposing the metal oxide back to its constituents, oxygen and the metal, which is part of why it's O2 that you get when you do this kind of thing. You're taking electrons out of the valence states. So you're weakening the metal-oxygen bond. That makes the movement of magnesium easier, or any other transition metal ion. So all that has to happen is that. I'll just do that again. If you keep an eye on these two transition metal ions, all they have to do, those movements, to create a nanovoid, a cluster of vacancies. Now, these two oxygens are not just going to sit there on their own. They're going to bond covalently to these oxygens to form two O2 molecules trapped in this void. And then when you discharge, when you put the lithium ions back in, they go back into these sites. Okay, they go, because the transition metals don't have time to reorganize. If you heat this up to a couple of 100 degrees, you can re-establish the honeycomb structure. But at room temperature, that doesn't happen. You repopulate here. You form a tiny little cluster of lithium oxide, effectively, with lithium ions going back in here. That's a different structure from here, a different arrangement. And so, of course, the energetics are different, which is why there's hysteresis once you've carried out this process. You're coming back along a different energy pathway to the one when you charged. So we can see that reflected if we do some DFT. If we do some DFT, here's the DFT, the energy on the Y scale here. The crosses represent the energies of different arrangements of the vacancies created when you remove the lithium ions. So at this point, we haven't formed O2. We've just charged our material, and we're looking at how, if we reconfigure those lithium vacancies in different ways, you can get slightly different energies. But the real prize comes when you create a vacancy cluster, one of these, this thing in other words, which allows O2 to be trapped. Then the molecular oxygens and the covalent bond, which is a big energy sink, drives the energy of this process down. It's this formation of the covalent bond which is really the driving force for this to happen. But to have it happen, it's a bit like being allowed to cross the street. You know, you've got to have the sign that says you can go. You have to have somewhere for those O2 molecules to go. And without those clusters, the O2 couldn't form, even though energetically it might want to. And as I said, lithium returns to a different set of sites, different energy, and that, again, we've done DFT on this structural transition as well as this one, and you do indeed get that 1 electron volt energy loss. So what this means is that we have a somewhat more unified picture of what happens in oxygen redox, because we've always known that when you oxidize oxide ions, you lose O2 at the surface. As I said initially, Mike Thackeray and Jeff Dahn, quite understandably, thought that was everything that was happening. It was all O2 loss. And then later it was recognized there was a lot of, if you like, oxygen redox going on in the particles. It now seems both those things are true. And the formation of O2 rationalizes all of those. So here's our cartoon of our pristine material again. This is the surface and this is the bulk, and of course it's the same when you start off. When you go through that oxygen redox, when you oxidize oxide ions, you lose oxygen at the surface. Probably the oxide ions form peroxide first and then O2 and then become evolved from the surface. As they do so, of course, the surface densifies. This has been shown before. You're losing lithium ions from this region. You're losing oxygen. You're densifying. And crucially, the surface, when it densifies, is essentially becoming stoichiometric. It's no longer lithium-rich. So when it reaches an NMC composition with no extra lithium, there's no mechanism for O2 loss anymore. And so the whole process sort of grinds to a halt at the surface. So the only other option now if O2 is to form O2 in the bulk, and that's only possible when you get this structural reorganization to form those voids. And as I said, the most stable, well, I didn't say this, but I'll say it now, the most stable forms of oxygen pretty much in the universe are in oxide ions or molecular O2, so it's not too surprising that O2 is formed. And again, we're really decomposing these materials because we're removing electrons from the valence band of the material, of the oxygen valence band. So we're sort of breaking up the oxide back to its natural constituents. This mechanism, or this process of O2 trapping, can also explain one of the other phenomena that's both intriguing and deeply annoying if you want a practical application of these materials, which is voltage fade. So I'm sure, as many of you know, when you cycle these lithium-rich materials as shown here, the voltage fades on cycling, changes on cycling. You would rather that didn't happen. It's got all sorts of unfortunate consequences for practical applications. So what we did is we used RICs to look at what happened to these materials as you cycle. So this is 100 cycles, and we've measured the intensity of the RICs at the top of charge and at the bottom of discharge, at the beginning, at the top of charge and after the full discharge. And basically what you see is a drop in the oxygen O2 signal with cycle number at the top of charge. So that's telling us that we're losing oxygen from the material. And as I said before, it was initially thought that happened, everything happened on the first cycle was O2 loss. It isn't, but you do always lose a little bit of O2 every cycle. The thing that really surprised us was that you can actually see O2 trapped at the end of discharge. Now, at the first cycle, I showed you all the O2 goes back to oxide ions. But gradually, as you cycle and cycle, some of that O2 is never reduced again back to oxide ions. It becomes stuck and accumulated in the structure. Both these mechanisms lead to voltage fade because they're removing oxygen redox, which is a relatively high voltage process, and replacing it to some extent with transition metal redox, which is lower voltage. And that's what causes the slippage of the voltage. And if you look in the stem at the material after 100 cycles, you can see it's really becoming quite porous. It's really getting quite large voids formed because you're sort of breaking the material up. And what happens is that these larger voids, where the O2 is trapped, you get more oxygen molecules in voids, they're larger voids, and some of them can't be reduced back efficiently to oxide ions. And I'll show you that in this. Here's the honeycomb structure again. This is what I've already shown you. Charging, the first cycle, you get your nanovoids with 2 molecular oxygens in each. Then you put lithium back in again. On the 100th cycle, you're getting voids that are much bigger with a number of molecules, oxygen molecules in there. When you discharge, you put lithium back in here, but of course the lithium ions tend to fill up these positions here, so you almost get a coating of just lithium oxide around the inside of the void, which of course makes electron tunneling to reduce the molecular oxygen even more difficult. And some of that molecular oxygen just doesn't get reduced back to oxide ions. And therefore you get this accumulation of O2 in the bulk. What of course this means is you can spend a lifetime coating lithium-rich materials, and many people have tried understandably to use this process to mitigate voltage fade perfectly reasonably. But based on this, you will reduce the amount of voltage fade by coatings, but you won't eliminate it because some of it is within the particles. So you've got to do something to stop this happening within the particles as well as suppressing O2 loss if you want to suppress voltage fade. So none of this we really want. We don't really want O2, and you don't have to have it. Here's a different arrangement, not honeycomb, from this compound here. Sodium again, but with lithium in the transition metal layers. And it's a ribbon structure, so not a honeycomb. And here's a reversible plateau. This is what we want. So in this case, we take lithium ions out of the transition metal layers, like this, and we put them back in the same place, so it's energetically reversible. So if you don't have the honeycomb structure, you can suppress the formation of voids, and therefore you can suppress O2 formation. And you're getting true oxygen redox. You're taking electrons off oxide ions like you can for transition metal ions without anything happening to the oxide ions apart from losing electrons. And here's this compound again. And again, we can look at magnetism to confirm this. Here's the magnetic moment for the pristine material. Here's after charging, after we've removed sodium, oxidized the oxide ions. We've oxidized 0.4 electrons per formula unit, so quite a lot of oxidation. No O2 formation. We have the same magnetic moment after charging. So if we were forming O2 with all those unpaired spins, we would see a change in the magnetic moment. We don't. And this is the sort of thing we really want to work to now. We don't want this material to decompose. We want to stop O2 formation. We want to move on now to think about how we can actually suppress that and focus on true O2. And that's where we need to focus, I think, for the field. That's where the field should focus attention. Let's move on to how we can avoid these problems. And, of course, what you also understand from this is that these electrons are delocalized. The reason you see no magnetic moment is, first of all, or no change in the magnetic moment, is, first of all, there's no molecular O2, so no unpaired spins. And the holes that you create are itinerant. You have delocalized electrons in the oxygen valence band, so they're polyparamagnetic. And the reason this happens is that's the process that occurs in our honeycomb, the rearrangement, harder to do in the ribbon, and also harder to do in this one here. So this is why this suppression occurs. It's harder to reorganize these transition metal ions to trap O2. Okay, very, very quickly, you can get oxygen redox in lots of other structures, not just layered compounds. Here's some disordered rock salts. This one here has oxygen redox capacity, and there are the classic vibrational peaks for molecular oxygen in the RICs. This one, with a different composition, another disordered rock salt, all of that capacity in this case is manganese redox capacity, and there's no evidence of molecular oxygen. So you can get this in DRX, or so-called disordered rock salts, but you can also avoid it. However, I want to move on to my second topic in the last 10, 15 minutes or so of the talk that I have. And that's solid-state batteries, in particular solid-state batteries with lithium anodes and ceramic electrolytes, because it may well be the only real way we are likely, if we can make it work, to be able to exploit the high energy density offered by lithium metal anodes, which of course would be a major advance. The big problem with lithium metal anodes, whether it's in liquids or polymer electrolytes or ceramics, is of course the problem of lithium dendrites. It shouldn't really be called dendrites in ceramics, but I'll still use that term. In the ceramics, it's fingers of lithium, filaments of lithium that penetrate even relatively dense polycrystalline ceramics when you charge the battery. So when you charge above a certain rate, certain current density, these dendrites form, pass across the ceramic electrolyte and short the battery, which is obviously catastrophic and needs to be avoided. So this is a virtual cross-section from an X-ray XCT measurement. In other words, this is a technique many of you, I'm sure, are familiar with, but it's essentially the same as CT scanning in medicine. You can create a 3D reconstruction of your battery, and you can take virtual slices and see what's going on. And this, in case, is operando. So here's the agiridite solid electrolyte. We have lithium metal on the top here. We have lithium metal on the bottom. And I'm going to run a movie here, and you're going to see the dendrite form up here and pass across the solid electrolyte. I want you at the same time to watch this. This is the voltage across this cell, this symmetric cell. And this, of course, is the point of short circuit. This is the point at which the lithium that will start here has reached the other electrode. And I want you to watch these two things, and you will see that the dendritic crack hits this other electrode before the short circuit happens. So let's do that now. So you see the dendrite. The lithium dendrites nucleate in pores, subsurface pores. They cause this effect called spalling. This is there you see we're already now at the other electrode, no short circuit. Crack here, only now does the lithium hit this electrode and you get a short circuit. So what this told us is that most of the models for dendrites had assumed the lithium was driving the crack in the ceramic at the tip. This suggests that isn't the case, and in fact we have to consider the dendrite process in two parts: the initiation of the dendrite and then how it propagates. Now I don't have time to talk about the propagation today. I'm just going to focus on the initiation part, but we've modeled both these phenomena. So this is what I'm going to show you is our model of how dendrites initiate in a ceramic electrolyte when you try to plate a lithium metal electrode. So, first of all, here the solid electrolyte is in orange here. The lithium is in this pale green. And any polycrystalline surface, even if you polish it, will have some crevices in it, some imperfections. And that's represented by these here. So when you start plating lithium, when you charge your battery, and you start plating lithium on here, the natural place for that to occur are these points here, okay? And then the lithium will grow down into these crevices. Remember, this whole thing is under stack pressure. So to nucleate lithium here is harder than to nucleate lithium here. So you fill these crevices first. Now, we've done a lot of Fib-SEM cross-sections of solid electrolytes with lithium metal anodes, and we see lots of features like this. So this is the lithium metals up here. This is the ceramic electrolyte. We see lots of features like this, these microcracks that connect crevices here to subsurface pores. So we represent that process by this in the model here. So here's the lithium. We're growing lithium. The cylinder represents the pore, and the sphere, represents the crack, and the sphere represents the pore. So you plate lithium here, it passes down this microcrack, starts at the crevice, comes down here, fills the pore, and we end up with this situation where the whole of this space, crack and pore, filled with lithium. Now this is when really the dendrite really gets going, because what is happening here is you're constantly trying to plate lithium at this anode. You're going to be reducing lithium now across the whole of the surface of this pore because it's filled with lithium, so it's got source of electrons. So you're reducing lithium ions from the solid electrolyte, and lithium atoms are trying to force their way into this space here. Now, lithium is a viscoplastic material. In other words, the model is basically one of hydrodynamic flow. Lithium is this buildup of lithium here. It's trying to release it by forcing lithium along the narrow crack, along this. So it's an extrusion process, a bit like squeezing a tube of toothpaste. It's hard because you have a narrow neck and you're trying to squeeze a viscoplastic material through it. So that builds pressure in here. So if you're plating at a high enough rate that you're forcing lithium in here faster than it can get out, pressure will build in this pore. It was always a bit of a mystery how a soft metal could crack a hard ceramic. But it's not the mechanics, it's the flow processes of lithium that are doing that. And once you reach a certain pressure, you will initiate a crack. And that is basically when the pore pressure, forget the stack pressure, is greater than the grain boundary fracture strength. The energy, if you like, that's holding the grains together at the grain boundaries. Once that's exceeded in the pore, you'll get a crack. So what we wanted to do then, of course, that's the physical model. We then wanted to relate the applied current density, the milliamps per square centimeter you're charging, to the flux, to the current, to the flux of lithium going into the pores in order to really be able to model what applied current you're going to start to get a dendrite. So you have to take account of a few things. First of all, that these pores are small, so you get field enhancement, current focusing, as you would normally get. The larger the pore, then the more current, so that's going to make it worse. We also have to take account of the fact that there's a distribution. There's not just one pore, but many pores. And that distributes the current density. So we have to take all of these factors into account in working out the relationship between the current and the pore pressure. And that's what we've done here. On the left, you see a plot of the pressure in the pore, versus the applied current. And these are the two modeled pressures as the current increases. The dotted line is taken experimentally from the grain boundary fracture strength. So experimental data goes into the model, like the pore size, which we get from SEM, the distribution of the pores, etc. This is also from experiment. The model then calculates the relationship between pore pressure and applied current. And this is done for two different pore sizes. This one is actually effectively no pore because it's the same radius as the crack, and this is for a pore with a 1.5 micron radius. And the point here is you can see that the pore makes things worse. The pore is the weak link. The pore means that you basically you can only get to a lower current density and then a crack. You want to get to the highest current density possible without cracking. Pores make things worse. Now, pores are the weak links. That's where the cracking process starts. But it's the whole microstructure of the ceramic electrolyte that you really need to take into account. I won't have time to go through all of these points, but I just want to make one or two comments because I know we want to get back on track a little bit here. It's the whole microstructure. In other words, it's not just the pore size and its distribution, but also the crack lengths and the widths. And unfortunately, when you densify a ceramic, not all of those things are going in the right direction to increase the critical current for dendrites. Some make things better, some make things worse. So it's not a given that if you densify a ceramic, things will be better. You'll make the pores smaller, but you'll also make the cracks narrower. And narrower cracks means extrusion is harder, which means pressure builds more easily. So it's a myth to think that densifying things is some kind of silver bullet. It isn't. But I will show you this one result. Here's the result for agirodite. Now, generally, the critical current densities, that's the current at which dendrites start, is set for many ceramic electrolytes, including LLZO, the famous oxide, at about 1 milliamp, maybe 2 milliamps per square centimeter. For practical applications, you want to be north of 5. You want to be above 5, maybe 7 milliamps per square centimeter. That's proved really difficult. With agirodite, here's the effect of densification. Normal agirodite pellets are about 83% dense that most people use. We've densified to 99%, and we've got a critical current of 10 milliamps per square centimeter. If you just look at these XCT images, this is plating 8 milliamp hours of lithium. That's about 40 microns of lithium, so no tricks here of tiny amounts of lithium. At 9 milliamps, a high current density, and no dendrites. So in the case of agirodite, you can indeed achieve this improvement in CCD by controlling the microstructure by densification. But it isn't true in all materials. Now, we have dug into the microstructure. We understand, and I don't have time to go through these. I just want to get to the acknowledgements. We understand why that is the case. And these are two cells, identical cells, cycled. The only difference is this is 83% dense solid electrolyte. This is 99% agirodite. Same current density. This one fails quickly. We stopped after 100 cycles because it was getting rather boring watching this at 9 milliamps per square centimeter. So there is an important correlation between microstructure and this big problem that's always faced this field of mitigating dendrites to make lithium metal anodes practical. Now, there are still lots of other problems to solve, but it's an intriguing correlation that may help us in the future. So I want to end at this point. I want to thank you very much for your attention. I want to acknowledge the support of the Faraday Institution under the Solbat program. Christina nicely mentioned it. A lot of this work was done under the frame of that program. The other funders, but also particularly my collaborators, research students and postdocs who, of course, have really done all the work. And thank you very much for your attention.
Thank you, Peter. And it was my fault that we were a little bit late. So, but I think we should at least have the possibility to ask a question. No, it was not easy to say. Ah, that was better. Anyone? Yes, please. You will have a microphone.
Thank you very much. So for the squid measurements with the susceptibility, was it the antiferro to para transition or something like that that you were looking at when you were extracting the Curie values at multiple in different samples?
So I think what we plotted there was the theta, the Curie constant. I can't remember now, it's about 2 or 3 years ago, at least, since we did that measurement. I can't remember the exact details as to what we saw. That was carried out at the lower temperatures. So the answer to your question is probably I can't remember, to be perfectly honest. But I have got a paper on my laptop, so if you want to talk to me afterwards, we'll go and have a look.
One more.
Hi. You mentioned about the densification of erythroid. And I'm working with LATP and LADP. So I was wondering, because you had not enough time to mention, what kind of ceramic electrolyte you say it's not direct, how it's called, that the more densities, the better. So you said it's not for all materials, it is. Can you elaborate on that a little bit?
Yes, sure. So, I mean, I should say we haven't looked at other materials in any detail. So that we were maybe lucky in working with the gyrodite because having done the modeling work, so what happened is we did the modeling work for the dendrite, trying to understand the dendrite mechanism. And then from that slide I showed you where you can look at what would improve the critical current densities. And we realized that some of those things are not going to happen with densification, like unfortunately the cracks are going to get narrower, which makes things worse. They're going to get, the pores are going to get further apart, which actually means that also makes CCD lower. So we then thought, well, let's look at what happens when you densify. Maybe we were lucky in using the gyrodite first, that it turned out to be an example where it does work. The sort of materials where it doesn't appear to work are things like the garnets, LLZO, because people have made them 99% dense and they still sit at around 1 or 2 milliamps per square centimeter. Now, I don't think we don't, and I don't know if anyone really yet knows why, but it's now interesting that we can look at the densification and say, it's really interesting that all of the things being equal, you might expect the densification to work. Now, it could be that in the case of LLZO, the cracks are really narrow. Maybe they're really narrow, and therefore the extrusion is really difficult, and therefore you build pore pressure at lower currents. Maybe that's the reason, and that's just a speculation, but we are, you might gathered, looking at LLZO now to try to understand the relationship between the microstructural changes on densification there. But that's why I say it's not universal, because we know that other things that are densified don't deliver that CCD, high CCD.
Thank you so much, Peter. I'm sorry I have to stop the questioning now, but you are here for the coffee break and the rest of the day, so you have ample opportunity to talk to Peter, and please do so. I think personally that when it came 2004, this Chris Johnson and Mike Thackeray paper, so wow, we can have cathode material 250 amp hours per gram, and then we became disappointed. And how long time it takes to show these really difficult, subtle, give that explanation, and how many methods you need. And the right methods really pinpoint that. And that's exactly what we are trying to sort of look at in Battery 2030 Plus. Not explicitly this problem, but how we can use the method. We have a little gift for you, so thank you so much.
Thank you very much indeed. Thank you then again. Thank you.
Yeah.